Hello my dear learners, in my last lecture I have started the very important topic as magnetic field, and continuing that particular topic I will discuss some of the very important laws, some of very important aspects and different theory of magnetic field. So, my today's lecture is dedicated to the Ampere's circuital law and its applications. So, let us start the Ampere's circuital law, because in the starting of magnetic field I have already discussed about the continuity equation, relaxation time, Biot-Savart law and some of the very different things which are essential and prerequisites for the study of magnetic field. So, we can study and we are ready to know about the Ampere's circuital law, because it is a very basic backbone to understand the existence of the magnetic field. So, let us start the Ampere's circuital law. What it says? Actually, this Ampere's circuital law is defined in the electromagnetic field theory for the existence of the magnetic field and basically the rotational and the circulation of the current density procedure which provides the existence of magnetic field around it. In electrostatics problems, generally the featured of a lot of symmetry, we were able to apply the Gauss's law to solve for the electric field and its different applications for getting the Ampere's circuital law. Likewise, in magnetostatics problems with sufficient symmetry, we can employ this particular law, which is more easily converted and applicable by using the Biot-Savart law as well. This law says that the integration of H around any closed path is equal to the net current enclosed by that path. This is the statement of Ampere's circuital law, and in the mathematical notations we can write that the closed integral of magnetic field intensity with respect to dl, which is equal to the I enclosed, means the current can be measured by applying the integration on magnetic field intensity with respect to its length, that length of the path, and this line integral of H around a closed path is termed as the circulation of H. The integral form of this law can be given like this: I enclosed is equal to integration of J dot ds, where J is the current density and ds is the differential surface area. So, by convention this ds is taken to be in the direction defined by the right hand rule applied to dl. Since volume current density is the most generalized term for describing the current density, we can also write that I enclosed is equal to volume integral J dot dV. So, the different forms of the Ampere's circuital law can be given in the form of line current density, surface current density and the volume current density. By applying the Stokes theorem into this Ampere's circuital law, we can also write that this H dot dl can also be written in the form of surface integral as del cross H dot ds, and this is written as I enclosed is equal to surface integral J dot ds, because the Stokes law must holds good for any surfaces we must have del cross H is equal to J. This is the differential form of Ampere's law. Very important equation, and it will be utilized in many of the applications and many of the theories of magnetic field further. What is magnetic flux density? The magnetic flux density B is related to the magnetic field intensity in free space by giving the equation as B is equal to mu H. Magnetic flux density is equal to permittivity of the medium multiplied by magnetic field intensity, where this mu naught, when this mu is represented as mu naught, it is known as the permeability of free space. Otherwise, in the general form, this mu is equal to mu naught into mu r, where mu r is the relative permeability and mu naught is the permeability of free space. The value of this mu naught, it is very important, and you must remember this, that it is equal to 4 pi into 10 to the power minus 7 Henry per meter. The different units of B, H or mu are also important, because from the mathematical notations you can derive the different units of any particular parameter, and the units of B are therefore Webers per meter square, but it is more instructive to write Webers per meter square, where Weber is equal to Henry Ampere. It is also important to understand the relationship between the Webers and Henry. But for generalized expressions, we can use the Tesla. Tesla is also a very important unit, which is described as Webers per meter square, and this is the standard unit adopted by the International System of Units. The amount of magnetic flux phi in Webers from magnetic field passing through a surface is found in a manner analogous to finding the electric flux, like phi is equal to integration of B dot ds, where B is the magnetic flux density. Okay. So, by using the different laws and different models, we can also define the magnetic field in these forms, like when we use the Gauss's law, the net magnetic flux passing through a closed surface as Gaussian surface, and that must be equal to 0, where it can be written as integration of B dot ds is equal to mu integration H ds cos theta, which is equal to mu cos theta, and integration of I, which is equal to 0. Simply, the algebraic sum of the currents entering any closed surface is 0. It is shown in the given figure. You can see here that the different currents are meeting at a point, and this is a closed surface, and the different these meeting point is known as the node. The Kirchhoff's law, when we apply on this, the same thing is here, that the algebraic sum of the currents entering any node is equal to 0, and here the sum of all the currents is equal to 0, you can see here. These are the analogous to the Kirchhoff's law and Gauss's law to the Ampere's circuital law. The boundary conditions, a very important topic for describing to get the exact value of magnetic field bounded by the different boundaries in form of linear, in form of surface, in form of volume. So, by using these boundary conditions, we can identify, we can calculate the magnetic field as well as electric field, because the boundary conditions are different for both these kind of fields. Here we will discuss the magnetostatic field boundary conditions. The special case for the boundary condition, if the surface current density K is equal to 0, we get Ht1 minus Ht2. You can consider here the figure, what the diagram is showing. The diagram is generally showing the different surface for the different mediums. Here you can see that medium 1 surface and medium 2 surface. Medium 1 surface is having the permeability in terms of mu 1 and the medium 2 is having the permeability in terms of mu 2. And when we identify the different boundary conditions for these two mediums, when this is the line which is joining the medium 1 and medium 2, we know that B is equal to mu 1 mu naught mu r into H, as I have already described about this particular term. What is mu r? Mu r is the relative permeability and mu naught into mu r is the term which is defining only the permeability of the medium. So, we can obtain here that Ht1 is equal to Ht2. These are the tangential components of the magnetic field and they are given in terms of like this, when Bt1 upon mu naught mu 1 is equal to Bt2 upon mu naught mu 2. And we also describe the existence of Bt1 and Bt2, that they cannot be equal to each other. And the tangential components of the magnetic flux density B, it is not continuous across the boundaries. So, this is a particular aspect of magnetic field for the different boundaries, where the medium 1 and medium 2 are considered for the different permeability as mu 1 and mu 2. Gauss's law for the magnetic fields, how it is applicable? We can see that integration of B dot ds is equal to 0. Here the diagram is given, and when these two surfaces are considered, you can see here, to find the second boundary conditions, we consider a Gaussian pillbox across the interface as shown in this diagram. We can shrink that particular delta H so that the flux out of the side of the pillbox is negligible, and here we can write it like integration of B dot ds is equal to integration of B n1 into an dot ds an plus integration of B n2 an dot ds multiplied by minus an. These are the aspects which are taken for the normal components, and when we consider this particular equation, we get the formulation in terms of B n1 minus B n2 bracket multiplied by that delta S, where this delta S is the differential surface area which is equal to 0. So, here we can say that the normal component of magnetic flux density B n1 is equal to B n2. This is the second boundary condition for the magnetic field. In this slide, I tried to convey the result of magnetic force. How can you apply the Lorentz force? How can you apply the Newton's second law, and how the magnetic field, magnetic force can be calculated by using these formulations. Everything is clear here. You can calculate, you can understand, you can put these equations step by step and get the answer. The calculation of the units is also described here. So, this is an example for calculating the magnetic force only. You can consider it. Next, come to the actual magnetostatics, how it works. Consider an infinite length in the form of a line segment, and this line segment is carrying a current density along the z axis, and we want to find the magnetic field everywhere across it. First, we inspect the symmetry and see that the field will be independent of z and phi and only dependent on rho. If we talk about the cylindrical coordinate system, and according to this Biot-Savart law, it says that magnetic field intensity H is equal to integration of I dl cross A r upon 4 pi r square, and this ideal is simply I d z a rho, and the vector from the source is to test point is r a r is equal to minus z a rho a r plus rho a rho. It means this is the simple calculation of the distance vector as r a r is equal to minus z a z plus rho a rho. This is the calculation of distance vector, nothing else. And in this form, this Biot-Savart law can be rewritten as H is equal to integration minus infinity to infinity. It means the length of that line segment varies from minus infinity to infinity, and this is given as I d z a z cross minus z a z plus rho a rho upon 4 pi z square plus rho square and whole to the power 3 by 2. This is the exact transformation of the Biot-Savart law, which is utilized and implemented on the calculation of magnetic field intensity for a line segment. This is the complete analysis, and you have to rewrite all these equations in the form of different vectors. So, if we talk about the magnetostatics or the magnetic field intensity derived for a infinite line current element, and here putting the different values of the different by applying the different laws, we can calculate, and the calculations are given in my slides. You can consider each and every point, each and every term for the calculation, because this is a vast theory and this is a vast calculations. So, you can consider my slides for calculating the magnetic field intensity for these particular aspects in terms of line current element, and here all the calculations are given here. We can calculate the magnetic field intensity as well as the current, and we find the magnetic field intensity resulting from an infinite length line of current, which is given here as H is equal to I a phi upon 2 pi rho. This is the result, and the magnetic field intensity H is proportional to 1 upon rho a phi, and the magnitude, the direction, both are resulting in the form of as the magnitude of the magnetic field is inversely proportional to radial distance, and the direction of the magnetic field can be found using the right hand rule, which is given in this slide. Come to the next, when we talk about the ring of current, the current distribution cannot be considered only in one single form of line current or in a line segment form. It is the second case where the magnetic field intensity can be calculated for a ring of current, and here we considered the ring of current, and for the calculation of this ring of current magnetic field intensity we use the Biot-Savart law formula, and we will replace the different components of Biot-Savart law by using the different other calculations and the different parameters. Likewise, here for the ring of current, this Biot-Savart law says that H is equal to integration of IDL cross AR upon 4 pi r square, and simply this is a very important factor, and this particular factor is denoted in the terms of differential segment. Likewise, dl is equal to a d phi a phi, and the vector drawn from the source to the test point, it is given as distance, radial distance r. This r a r is given as h a z minus a rho. The calculation is given here, the magnitude is given like this, unit vector is given like this. So, by replacing all these terms, all these parameters in the Biot-Savart law, we can define the magnetic field intensity for the ring of current, and this is the whole geometry and the calculations by putting the values in the Biot-Savart law, and this is the whole calculation. You can understand this diagram by placing the different values, by putting the different calculations on the formula, we can get the magnetic field intensity. This is the third case of a solenoid. The magnetic field intensity of a solenoid can also be considered, and when these solenoid are many tons of insulated wire coiled in the shape of a cylinder. For getting the magnetic field intensity for a solenoid, we consider, suppose the solenoid has a length h and a radius a, and it is made up of n turns of current carrying wire. For tight wrapping, we can consider the solenoid to be made up of n loops of current. To find the magnetic field intensity from a single loop at a point P along the axis of the solenoid from we have. So, generally the formula DHP is equal to DIA square upon twice of Z dash square plus A square whole to the power 3 by 2, and it is in the direction of AZ. It is the magnetic field intensity at the distant point P, and this is in the direction of Z only. So, you can consider here the differential current, it is equal to n upon h I dz dash. In the same manner, fixing the point P where the field is desired, this Z dash will range from minus Z to plus Z, and here we put the limits on the integration and can define the magnetic field intensity like H is equal to N I upon H A Z. So, simply we have described the magnetostatic field, its calculation for the solenoid, for the circular ring, for the line segment. Now, Ampere circuital law application to current sheet. When a sheet which is carrying a current, how we can consider, how we can apply the Ampere circuital law. You can see in this slide that the path which is followed by the current in a sheet is considered here and the Ampere circuital law is implemented here. Now, the Ampere circuital law application to the current sheet, how it can be calculated. In the last slide, what we have seen that the path taken by the current is described in terms of the Amperian path, and when Ampere circuital law is applied on that path of current, we can calculate the overall current in terms of like overall current in the form of like this, whatever you have seen in the previous slide, like this I enclosed, and this I enclosed is given as integration of h dot dl, and the different segments of dl are considered as A, B, C, D in that particular form. Here the overall calculation of this I enclosed is for the different segments A to B, B to C, C to D, D to A, and here the different components which will exist are given and the other components are nullified. So, this is the exact equation, and now final formulation of these magnetic field and electric field is given in terms of Maxwell's equations, and Maxwell's equations in the form of electromagnetic waves and its propagation. This is the theory which is the resultant of the whole study of magnetic field and electric field. Generally, the two kind of fields, scalar field and vector fields, are considered for the study of electrostatic field and magnetic field. Now, we will consider the potential, magnetic potential in the form of scalar and magnetic. Scalar magnetic potential is analogous to scalar potential in electric fields. It means the magnetic field vector is the negative gradient of the scalar magnetic potential, just as the electric field vector is the negative gradient in the electrostatic potential. Magnetic vector potential A is the vector quantity in classical electromagnetism, which is defined so that its curl is equal to the magnetic field, and together with the electric potential phi, the magnetic vector potential can be used to specify the electric field E as well. This is a very important theory which will be used in the antenna and wave propagation, where we will study the generation, the production of electromagnetic waves from a conducting element like antenna. In that case, we will consider this scalar potential and vector potential individually, where the magnetic field will be responsible, magnetic field will be produced with the help of vector potential, and the electrostatic field is produced with the help of scalar potential. Okay. So, next these are some of the calculations which are important, where the cross product of del cross H and del cross E, these are given for getting the different Maxwell equations, and different scalar and vector potentials are considered for the different calculations. This is the theory, this is the mathematical formulations, this is the complete derivation, and you can understand each and everything whatever I have already described. So, kindly go through these slides and you will get all the answers by studying all these things. If you consider the electrostatic field, if you consider the magnetic field, all the answers of the existence of scalar and vector potential you will get the answers for each and everything. So, I think that all the things have been covered in this lecture, and the Maxwell's equations will be studied in my next lecture. Thank you very much.